Good afternoon, everyone. Today we will start with distributed feedback lasers. There are various categories of lasers, structures of lasers. One is distributed feedback laser. Then we have distributed Bragg refractor, tunable lasers. And vertical cavity surface emitting lasers. So first we will discuss distributed feedback lasers. So this is the structure of distributed feedback laser. In this, there is an active region between an N-type and P-type layer. And in P-type layer, there is a grating. There is a corrugated grating, and this corrugated grating is along the complete length of this laser. So this corrugated grating provides the variations in the refractive index. Basically, it works as a reflector. As earlier, there is a cavity in the laser, but here this grating grating reflects particular wavelengths of light and transmits all other wavelengths. So if we have this kind of structure. Yes, this is the corrugated grating. So it reflects particular wavelength of light and transmits all other wavelengths. Grating reflects only those signals which is having a wavelength nearer to the Bragg's wavelength. So, like your mode is traveling, it is reflected from here. Mode is traveling, it will reflect from here. Again, mode is traveling, it will get reflected from here. So using distributed feedback laser, only one mode is possible. In this, we will get only one mode, and that mode is having single frequency, and all other frequencies will get suppressed. And in this case, the high gain is obtained. And in distributed feedback laser, the feedback is distributed all along the length of the laser. And these two ends are AR coated anti-reflection coated. These two ends. This is your P type and this is your N type. In this case, these two ends are acting as an they are anti-reflected AR coated. Then after that, in this, there is no cavity as such. However, the structure sports a mode. Suppose this is your guided mode. This is your guided mode, which is traveling along the length. And in distributed feedback laser, there is a grating. And this grating is a corrugated grating or a periodic structure. And the mode which is propagating in this direction, the mode is propagating in this direction, continuously see reflections at these corrugations. So these are the corrugations. The mode which is going in this direction gets reflected continuously, and feedback is distributed all along the length in this case. So these are fixed frequency lasers, as we can't tune them to other wavelengths. So these lasers are the fixed frequency lasers. And if let's assume that this corrugated grating looks like this. In this, we have a corrugated grating is nothing. It is a variation of refractive index. Suppose here refractive index is high, then refractive index is low, then high refractive index, then low refractive index. and mode is traveling like this. So first we have high refractive index, then low refractive index, and the mode which is propagating in this direction, it encounters a periodic refractive index variations. As it will travel in this direction, then it will encounter a refractive index variations like n high refractive index and low refractive index. So as it is traveling in this direction, when it encounters a refractive index variation, it gets reflected. Further it will travel, it will get reflected like this. And now the mode is undergoing a periodic reflection at the interfaces as it travels through towards the right side. So for simplicity, we can also express the refractive index variations like a step variation. See, here you have a high refractive index, here you have a low refractive index, high refractive index, and again then low refractive index. And mode is traveling like this and it will suffer reflections. We travel like this and it will suffer reflections. Suppose this distance is lambda by 2 and this complete distance is lambda, and this is your nz refractive index. And suppose mode is traveling in z direction, see mode is traveling in z direction and nz is the refractive index. Then a ray is reflected from the interfaces. It is getting reflected from these interfaces. The reflected wave comes back, and like from here it gets reflected, the wave is coming back, and both of them gets joined, and the ray will get resonantly reflected. The ray which gets reflected and comes back, it adds phase. If it adds phase, then there will be a coherent addition. See, wave is traveling in this direction, it gets reflected like this, and then it gets joined. And if it adds phase, then there will be a coherent addition. Coherent addition will be there, and you get reflection, high reflection for those wavelengths. Then the wave, suppose the wave k, suppose the wave vector k naught and n is the refractive index, then for the round trip, it is expressed as 2 into k naught into n into lambda by 2. And lambda by 2 is the thickness. See, it is traveling, then it is getting reflected. As it is a round trip, that's why it gets multiplied by 2. K naught is the wave vector, n is the refractive index, and then lambda by 2, I've told you, is the thickness. So delta phi is the phase difference between the wave traveling and the reflected wave. This delta phi is the phase difference between the wave traveling and the reflected wave. So this is low refractive index, this is high reflective index. So there, suppose there is a additional phase change of phi here, then del phi is expressed as 2 k naught into n into lambda by 2 is equal to pi. The wave which is coming back, suppose this is A point and this is B point. The wave which is coming back from point B is in phase with wave which is reflected at point A. See, one wave is reflected from this point and another from this point. The wave which is coming back from point B will add in phase with the wave which is reflected at point A only when above condition is satisfied, only when this condition is satisfied. So del phi is written as 2 k naught into n into lambda by 2 is equal to phi. 2 by 2 gets cancelled. Then 2 pi by lambda b into n into lambda is equal to pi. I have substituted the value of k naught. It is 2 pi by lambda b, where lambda b is the Bragg's wavelength and k is your propagation vector. K is equal to 2 pi by lambda. Here I am writing lambda V, which indicates Bragg's wavelength. Now, if n is the refractive index of the medium, then wavelength lambda V will get resonantly reflected. This wavelength will get resonantly reflected and will get added in phase. So, if this is the reflection spectrum of this structure, this is the lambda. This is the reflection spectrum of a structure. See here I'm writing reflection R and this is lambda. Then we have lambda B. These are the side lobes. Side lobes because of the Fourier components, because of the step-like variations. So we will only get one frequency in case of distributed feedback laser. And corrugation or a periodic why we have a how we can obtain corrugation or a periodic refractive index variation means, see, this is the corrugation. Now the why we have refractive index variations, how we can obtain the refractive index variations means both the materials that we have used here and that we have used here are different. And in this case, the periodic structure gives continuous feedback all along the length. There is no reflection from these ends because these ends are the AR coated, anti-reflection coated. So there is no reflection from these ends. But being a periodic structure, the reflection is wavelength selective. What it means? Wavelength selective means only one particular wavelength which will satisfy the Bragg's condition. Bragg's condition is lambda V is equal to 2 in lambda, will get resonantly reflected as the mode goes in this direction. So this is the Bragg's condition. The wavelength which will satisfy this condition will get continuously reflected. So this is all about the distributed feedback laser.